Hello, welcome to the Halloween special. Yeah, that's right. Today we're talking about phase. Viewer discretion is advised. Does this sound familiar?
Bro, don't use the stock EQ. It doesn't even have linear phase. Trust me, bro, if you don't use linear phase, you'll mess with the phase too much.
Joking aside though, the word phase can sound kind of big and scary to a lot of people, especially if they don't really know what it is or what's going on. And you can kind of waste a lot of time going down the wrong paths and worrying about the wrong things and trying to fix things that don't even need fixing. But the basic concept of phase in audio production is actually pretty darn simple. I'm guessing most of you know this, but all sounds are waveforms, right? And all a waveform is really just a graph plotting time on the x-axis and amplitude on the y-axis, with the center of the graph being 0 decibels, so silence, and the tops and bottoms being max amplitude. And the frequency of the wave is literally just how long it takes to complete one cycle of that graph. So it's how fast this waveform is repeating in time. And you can have simple waveforms like sine waves, or you can have multiple more complex waveforms that all come together to create an even more complex waveform. No matter how complex that waveform is, though, the building blocks of that waveform is always going to be individual harmonics or sine waves. All phase actually is how far through its wave cycle a waveform is at any given time. Let me explain a bit further. You're likely to see phase expressed in one of two ways, either in milliseconds or degrees, like angular geometry degrees, because, degrees Celsius would make 0 sense, and that would be stupid. So say, for example, we have a sine wave, and maybe it's repeating at 55 times a second, so 55 hertz. And say, for the sake of example, we had like a sonic camera, then we could take a picture of that waveform at any given point in time, which is physically impossible, but bear with me for a sec. If we took a snapshot of that waveform and it was right at the start of its wave cycle, we would say it has a phase value of 0 degrees. And if it was right in the middle, we would say it has a phase value of 180 degrees. If it was right at the end, we would say either 360 degrees or 359 degrees, depending on how you've set the graph up. So note that 360 and 0 degrees is actually the same value because we've looped all the way back to the start and the waveform has started repeating again. And so the values at each sort of like quadrant, so the little quarter marks, would be like 90 degrees and 270 degrees. It could also make sense to define the center as 0 degrees and the start of the graph as negative 180 degrees and the ending as positive 180 degrees. Either way, it adds up to 360 degrees total, and you will see phase measured and expressed in both ways. It just depends on the context. And you could also measure these points in milliseconds instead of degrees, except the downside of that is you'd have different values depending on how fast the waveform is repeating. So different frequencies will have different millisecond amounts. So this degrees measurement is just more of a standardized way of thinking about a waveform's phase. So I've got this basic sine wave oscillator here in phase plant. And as you can see, phase plant actually has a dedicated phase parameter for each oscillator. So we can change the phase offset. This is what this is called, changing the phase offset, since we're offsetting the phase compared to its default position. And in phase plant, it goes from 0 degrees in the middle, like we said before, and then it goes down to negative 180 and then up to positive 180. And when I tweak this value, you can actually see the waveform moving forwards and backwards in time. And all we're really doing is see right at the start here, this is where the waveform is starting. All that's effectively doing is just changing the point at which the waveform is starting. So we're changing the wave's starting position in its wave cycle by changing this phase parameter here. Now, if I start at 0 degrees again, play a bunch of notes and change the phase of those notes, try to use your ears and see if you can pick out any sort of changes in the actual sound. So when we change the phase offset, or the phase rotation is another way to put it, since we're changing the degrees, like degrees in a circle, right? Even though there's nothing actually rotating, that's just how people describe it for some reason. There wasn't really much change in audible like frequency or really anything. There wasn't really much change at all. The only real change was that when we were at values like negative 90 degrees or close to it, or positive 90 degrees, the waveform is starting at this sort of max amplitude state. So we get more of a click when the waveform starts. But other than that, literally sounds exactly the same. However, that's not the full picture. So what if I hold down a note this time and change the phase while I'm playing the note? Now, there will probably be some weird sort of digital artifacts, but try ignore that and just see if you can hear any other sort of changes in the waveform sound. If you've got decent ears, you probably should have heard that the waveform was actually changing in pitch slightly. And when I actually started changing the phase rotation faster, that pitch modulation increased. But as soon as I stopped changing the phase rotation, the pitch modulation stopped. If I add a spectrogram here and go down another octave, the effect is probably even more noticeable. No pitch modulation. I'm going to start moving the phase slowly. And I'm going to increase the speed. You can really see that pitch moving. Basically, by actively changing the phase of a waveform while that waveform is still oscillating, we're effectively squishing or expanding the waveform in a way, right? It's similar to like the Doppler effect. If you've ever heard a car come towards you real fast and the pitch goes up and then it goes away and the pitch goes down, it's because the waveforms are being compressed and expanded. So by compressing and expanding the waveforms like this, effectively we're just changing the pitch, because by definition, smaller waveforms are higher in pitch and larger waveforms are lower in pitch. But generally, we probably wouldn't be modulating the phase value much if the waveform is oscillating anyway. So if changing the wave's phase offset actually makes little to no difference to the waveform sound at all, unless we're moving it, why does it actually matter? Well, it actually matters for a lot of different reasons. Hopefully this isn't news to you, but with music, we often have more than one signal playing back at the same time, right? And that's when phase offsets actually becomes extremely important. And just to illustrate that, I'm going to copy this oscillator over. And so now we have two oscillators both playing the exact same note and both having the exact same waveform. If I mute this one, play a note, and then enable it, you should notice that the waveform actually gets like twice as loud. So what's happening here? Well, if you remember your like high school physics class, waves that line up perfectly. So for instance, these peaks and troughs, they're both lining up perfectly, right? And when that happens, you get something called constructive interference. And all that means is these waves are actually getting added to each other. So at this point here, this wave is at plus whatever dB, say for instance, plus 7 dB. And then this wave is also at plus 7 dB or whatever. Those values actually get added together. So we get a value of like plus 14 dB out the other end. It wouldn't actually be 14 dB, it'd be 10 dB because decibels aren't a linear scale. But just for the sake of argument, to get the point across, we can imagine it like that, right? And same with these little troughs here. They also get added together, except they're negative numbers. So we get even more of a negative number. And that just basically means more amplitude as well. Because remember, silence is actually 0 dB right in the center. So this is just a property of waveforms and how they work. And so no matter whether you're working with synthesizers or recorded audio or whatever it may be, there's always going to be a little bit of phase cancellation or constructive interference or whatever, unless you're only working with one sort of single sine wave. The trick is knowing when it's sort of affecting your kind of desired result negatively. And once you have this knowledge, it can definitely be a like pretty cool sound design tool to sort of use and abuse as well. And just to get my point across about how this is applicable to all of audio production, not just synthesizers, I'll just record the sine wave down. I'll mute the phase plant track. So we're only left with the audio here. I'm just going to duplicate the audio, and I can offset the phase of one of these waveforms exactly the same as what we're doing in phase plant, simply by just dragging the waveform forwards or backwards, and we have the exact same effect. So right now we have two sine waves that are exactly the same, so we should expect constructive interference. So I'll mute one, play it back, and enable one. It should get twice as loud, which it does. And now if I try to line up these peaks and troughs so that they're completely opposite, we should expect them to cancel out a bit. Now this might not be absolutely perfect because we would have to cancel out pretty much to the sample here, but this should be way, way, way quieter, right? And I could line them up a bit better here. Yeah, so that's destructive interference. So notice that even though our levels on the meters here are still staying the exact same, if we look at the master here, it's going way down. So this is just something you need to be aware of as an audio engineer and as a producer in general. And there's actually devices and plugins made for this exact purpose. So just offsetting signals by the tiniest amounts, like for instance, Ableton's stock align delay is made for this exact purpose. And we can either offset by time, samples, or distance. Now you might be wondering about distance, since sound has a finite speed and it's actually relatively slow. So like sound travels through the air, right? We're just measuring how much this offset would change the waveform's position in space. So it's pretty interesting. So if I choose samples here and then link the left and the right channels, I should actually be able to offset this bottom waveform enough so that it almost perfectly cancels out. So around about 138 samples there. So that's almost perfect phase cancellation. And then there's other third-party tools for this application as well, like SSL's X-Phase, which also has sample-based delays here. And it also has frequency-based phase correction as well, which we'll get into in a bit. And there's also another really good third-party one called Time Align, I think it is. That one also looks really good. So we're starting to see how phase rotation and offsets can really actually drastically affect the way a signal sounds. And you've probably actually been using phase interference to your advantage this whole time without realizing it, because it's actually how a lot of your favorite effects probably actually work in the first place. Things like phases, choruses, flanges, delays, EQs even, filters. All these effects and devices actually use phase offsets, either to create their sound or as part of their sound. So for example, why don't we make our own flanger? So back here in phase plant, just got a saw wave. If I duplicate it out and then modulate the phase of the second saw wave, you can start to hear it actually just sounds exactly like a flanger. Because that's how flangers work. So if we add a LFO here, attach it to the phase, and then maybe just slow it down a bit, we've got our own flanger. Now, phase offset isn't actually the only thing that can cause phase cancellation or phase interference. So if we get rid of this phase modulation here, so we just have the two separate saw waves, we can actually cause phase cancellation just by changing the pitch of one of the saw waves ever so slightly. So for example, you can hear that? It's a similar kind of sound, right? This is actually exactly how chorus and unison works. And it's actually a super, super common thing to use when you're trying to make like respaces and stuff. So if we go back a couple octaves here. Yeah, so it already sounds like a respace, right? Especially if we duplicate it again, and I'll set pitch of this one even more. And then we like add a low pass filter or something, and maybe change the panning of these slightly too. That's a respace. Now, EQs and most phases, on the other hand, all work by changing the phase rotation of specific frequencies in the signal. I'm going to link in the description to a really, really cool little blog post that I found about a guy kind of explaining how it works a little bit. But for example, with this filter, which is basically just an EQ, right? They both work the same. In super basic layman terms, the computer is basically just splitting our signal up into multiple different signals, and they're all slightly delayed from each other. And it's able to sort of cancel specific frequencies or boost specific frequencies more than others, pretty much using phase cancellation. Now, there is a little bit more to it than that, but that's all you really need to know unless you really want to actually just make your own filter or EQ, I guess. Now, obviously, we're not actually hearing multiple different signals. We're just hearing the effect that all this is having on our source signal. And actually, the end result of putting a filter or an EQ on our source signal, other than that, obviously the frequencies get sort of attenuated or boosted, is that there will actually be a slight phase shift around the frequencies that are being sort of attenuated. So for example, with this low pass filter here, the phase rotation of the frequencies sort of around this area here will actually get more and more and more until it gets to sort of the steepest part of the cutoff. And then past that, obviously the frequencies are getting more and more attenuated, so you can't hear the phase shift as much. And then for example, with like a little bell boost here, the phase shift is even less with these types of EQ boosts and cuts, but the phase shift is sort of highest around these steepest parts of the bell curves. Now, these phase shifts are actually extremely hard to pick out with your ears. They're like almost negligible in terms of like actually being able to hear the difference. That is except for like super specific circumstances, but we'll get into that a bit later. I'm going to get rid of this filter and these extra oscillators, and let's actually dive a little bit deeper now into phase rotation and phase offsets and things. So if we actually make this generator and phase plant here into a wavetable generator, now we're actually able to click this edit button and we get this really fancy, intimidating looking window. This is just the wavetable editor. Now, I'm not going to go into how wavetable editors work, really, but I just wanted to go into this window because it's really good at illustrating what I'm about to show you. So right now, our wavetable is just outputting a static sine wave, right? But in this wavetable editor, we actually have the ability to go in and add extra harmonics to the sine wave. So we could add the third harmonic. So this is just adding a second sine wave. Basically, that's 3 times higher in pitch than our original sine wave. And it's represented by this big sort of blue line here. And we could add like the 5th harmonic, which is just another sine wave. If I move this over a bit, you can actually see our waveform that we've created here. And you might have noticed these little sort of clock-looking knob dial thingies down the bottom here. These are actually phase offsets for individual harmonics, which is really neat, right? So we're actually able to offset the phase of different harmonics separately. And you can actually see it represented in this waveform visualization there too. So if I move this 5th harmonic around, you can actually see it moving. Maybe the 2nd harmonic. And so remember that all sounds are built up of sine waves, and the timbre of a sound, or the sort of the tone of a sound, is determined by, one, the sort of placement of the harmonics, where they are in the audio spectrum, and also the amplitude of the harmonics, how loud they are. But there's also a third thing, which we've just discovered here, which is the phase of the harmonics. And that's actually also important for changing the tone of a signal. Now, it's definitely more subtle than frequency and amplitude, but it can definitely make a difference in the tone. It's most noticeable in these small amounts for really basic sort of subby tones. So maybe you've only got 3 or 4 different harmonics. By changing the phase of one of the harmonics, you're just able to get each harmonic sort of sitting a lot nicer in the waveform. And it can really make a big difference in getting the sort of subtone nice and fat and thick. But for instance, we could also have a more harmonically dense sound, like a saw wave. We can actually see all the individual harmonics here now of the saw wave. And we're actually able to change the phase of the first few harmonics too. So like I said before, changing the phase of individual harmonics makes a pretty subtle difference to the sound, especially with these more complex waveforms. But what if we change the phase of all of the harmonics at once at different amounts? Well, basically, if we go into the effects here, that is what this disperse option does. It offsets each individual harmonic a little more than the last one, right? And the effect on the sound is actually huge. So if I enable this, I've just put the disperse effect on the saw wave. It's at 0%, so it's doing nothing. If I go down an octave maybe. Now, if I bring it up, you're actually going to hear a huge difference. But remember, theoretically, we're not changing the amplitude or frequency of any of the harmonics. All we're changing is the phase here, and you're going to hear a massive difference. And we could go to negative values too. So this compared to that is a huge difference, and all we've done is change the phase of all of the harmonics in different amounts, and it almost sounds like gloopy or like liquidy, which is really cool. And there's actually plugins that can do this to any audio signal, so not just synthesizers but anything. And if you remember back when I showed you SSL X phase, we had the frequency dependent phase offset. That's basically the same idea here. So this graph is just showing how much each frequency is getting offset. So if we were to have it here, like 125 hertz would be like fully offset, and then it snaps back up here. Notice that this is measured in degrees. Negative 180 and positive 180 are actually the same sort of value in terms of phase, right? So it looks like it's like all of a sudden switching phase alignment, but really it's the same. It's just more of a smooth change in phase. But this is the same idea, right? So you can kind of hear it there. If we bring this Q value up a bit, it might be a bit more obvious, especially in the higher register there. These types of plugins actually work in the exact same way that EQs do. So this sort of phase offset shape is exactly what would be happening with a low pass filter or a high pass filter or whatever. The difference is it's doing all that, except it's just not attenuating the frequencies. So we're still hearing the full spectrum. And also the phase rotation is way more pronounced than it would be with any normal EQ. Another popular VST that does this kind of thing is kilohertz disperser. So this graph is literally just a graph of how much we're displacing the phase offset of each frequency. So this is 130 hertz or whatever there. And so below 130 hertz, we're really displacing the phases, and then it sort of trails off. And we can sort of pinch that phase offset too. So now we're really focusing on that cutoff point. And another one that does the same sort of thing is M freeform phase. This one is actually free, and it's probably the most extreme one of the three. You can get the most crazy phase offsets and stuff with this one, and you can literally just draw in the phase offset amounts, and you can right click and change it into more of a sort of parametric EQ style of interface too. Now this one actually introduces a little bit of latency because it also shifts the phase backwards in time as well as forwards in time, whereas things like disperser only shift the phase forwards in time. So we can do some really, really crazy shapes with freeform phase here like this. Put it on extreme mode because, you know, why not? But the real power of freeform phase is it has this depth knob, which really allows you to go like beyond 360 degrees of phase rotation. So you can go from like 100%. So these values are sort of accurate here. But if you go up to like 200%, they're all doubled. And you get crazy sounds. Bear in mind, we're not changing the frequencies or amplitudes of any of the harmonics. We're only changing the phase. Now, if we go back to normal parametric EQs here, like I said, they work in the same sort of way. The phase difference is just way, way, way less pronounced. And you'll typically only hear this phase difference when two things are happening. So both if the frequency boost or cut is like really, really extreme, like something like this. And if that boost or cut is moving around lots, that's when this phase offset will be the most noticeable. So really, both of those things have to be happening for phase offset with normal EQs to be noticeable. But also to be 100% crystal clear, I'm not saying that if you can hear the phase offset, that it's a bad thing. It might, in fact, be exactly what you want and sound kind of cool. And just like in the start of this video, when I moved the phase offset and phase plant slowly, and the phase offset pitch modulation kind of sound was less noticeable. It's the exact same thing with EQs. The slower the modulation, the less noticeable it is, because it's the exact same kind of effect that happens. So I can actually show you what I mean. So we have a spectrogram here again. So frequency is on the y-axis, time is on the x-axis, and we're still playing with saw waves. If I make a boost in the saw wave, I don't know, around 700 hertz. It's a really big boost, right? I can't really hear any sort of noticeable phase shift effect though, right? Especially if you bring it down, it would be even less. Even if I bring it all the way up and change the Q value so it's really thin, and it's a sharp resonant peak, I still can't really hear any sort of noticeable phase shift happening. But now if I start moving this resonant peak around, you can see on the spectrogram here, we get all these sort of weird little bloopy bits. And it's actually pretty noticeable. So if I just hang around near the fundamental here and just wiggle it around, you can see the fundamental is actually just modulating its pitch quite a lot. And when we bring this resonant boost up and down, it's actually sort of pulling and squishing the frequencies up and down with it in a way. But again, it doesn't really sound that bad, really. It kind of actually sounds pretty cool, to be honest. And if we do the same thing with the cut instead of a boost, you sort of see the same thing is happening. You kind of hear it too, but it's a lot less noticeable since we're actually cutting those frequencies that we would otherwise be sort of phase shifting anyway. It's a lot less noticeable. And this is actually why you'll hear a lot of people saying, you should never boost with a digital EQ. They shift the phase too much. You should only cut. Well, the funny thing is that even analog EQs have this exact same effect. Plus, as we discovered, it's only really an issue if the EQ shape is 1, really extreme, and 2, moving around lots. Hey, sorry, just a quick little intermission here. I'm just editing the video and I realized that I forgot to mention one instance where phase shift can actually be kind of noticeable and it might be important for you to know about. And that is with high pass filters. So for instance, if we have another saw wave again, if I enable this high pass filter, you can actually see it's changing the waveform shape of that saw wave quite a lot, right? Even though we're nowhere near the fundamental frequency of the saw wave. And the change in timbre is actually quite noticeable. So my suggestion would just be to avoid any unnecessary high pass filtering when you can, even though most of the time when you're high pass filtering it's going to be a net positive because you're reducing unwanted frequencies to make your mix cleaner. But this is probably most important with super loud genres like tear out or dubstep or something like that. Having asymmetric waveforms, especially in the bass area, is going to make it a little bit harder to get your tracks to a louder and louder LUFS or master level. So just be aware of that for sure. It's usually not the end of the world, but yeah, back to the video. By the way, this effect is also super noticeable with high and low pass filters, right? You can really see these sort of frequencies moving around a little bit instead of staying static, especially if we boost the resonance, it'll be even more prominent. We can even make this effect way more noticeable with Pro Q3 since it has a brick wall filter mode for the high pass. You can really see those harmonics being squished and pulled and But again, it doesn't sound bad. It just sounds different and kind of neat. Plus, this is also an extreme example. Most people, if they're using a brick wall filter, they wouldn't really be moving it around lots. They would be using it to sort of cut really specific frequencies. But you can also even hear this phase shift effect with the brick wall filter. Since it's so extreme, you can even hear it when the filter isn't moving. So even when it's static, you can see it on the spectrogram here. That fundamental, which is around this cutoff point, sort of trails off. And if we put that cutoff right next to it, you can really hear it. It almost kind of sounds like someone's gone into the synth and like brought the release up a little bit, but only on the sort of fundamental frequency there. This effect is actually called post-ringing, but it's hardly noticeable, if at all, with normal sort of filter shapes and movements, although you can sort of trade it for something called pre-ringing if you change the EQ into linear phase mode. But linear phase mode actually has a whole bunch of its own problems. Like I said, it's got pre-ringing, and that pre-ringing, since it's transferring energy from the start of a signal to before the signal's even started, it actually sort of softens the transients out a little bit. So if you have really punchy drum kit recording or whatever, and you've heard that, oh, you should never EQ a recorded drum kit unless it's with linear phase, and you're doing drastic changes like this, and then all of a sudden your drum kit loses all of its punch. Well, it's because of this sort of pre-ringing and the softening of the transients and stuff like that. Plus, linear phase EQs also introduce quite a bit of latency, so they can be really annoying to work with sometimes and require a little bit of extra sort of CPU power. And if you use a whole bunch of these throughout your whole project, the latency is going to get very, very noticeable, almost to the point where it's like impossible to do anything. If you wanted a more detailed explanation on linear phase EQs versus minimum phase EQs and all that, definitely check out this video by Dan Morrill. He did an amazing video on FabFilter's channel, I think, and it explains a lot. But for now, I'm going to go back to the normal zero latency mode. And just to get my point across about how, even though this phase shift here is the most extreme scenario that you could possibly sort of manufacture to actually hear this phase shift that happens with parametric style EQs like this, it's not necessarily a bad thing. And I can actually show you that by comparing this sound to a high pass filter that actually has zero phase shift. So we can actually fairly compare what this would sound like with zero phase shift. So I have the saw wave in Vital, and if I bring this brick wall filter in, it sounds exactly the same as before. Lots of phase shift. I'll disable it for now. The latest update in Vital actually introduced these spectral style filters. And what these actually do, so if I go into the high pass filter, this is a spectral high pass filter. And this is actually working with the wavetable generator here. But instead of shifting phases of the harmonics and stuff to sort of cancel them out, it's just simply going into the wavetable generator and turning each harmonic up or down or whatever as needed. So there's zero phase shift involved in this process. And if I start really low and bring it up and do a big sweep like I did with Pro Q, you can hear what a zero phase shift high pass filter would sound like. You can see on the spectrogram, all of the harmonics are completely stable. You know, it's kind of funny. Zero phase shift with a spectral high pass almost sounds more digital. And Pro Q with all of its phase shift actually kind of sounds a little bit more natural. And it's like got this weird sort of snarly, liquidy sort of sound to it. I actually kind of prefer it, to be honest. I don't know. Neither are bad. They both sound fine. And yeah, if you're really, really super paranoid about the exact frequency that your saw waves harmonics are at all times, then you probably want to use the spectral high pass. And things like this can actually be really useful for making your own wavetables. The cool thing about these spectral filters, though, at least in Vital, is that you're able to actually go in and make your own custom filters. So you could make crazy, crazy shapes that you probably would never do with a normal EQ. So hopefully by now you're really starting to understand what phase shift is and why it sometimes is important, sometimes why it isn't important. Here's a few more situations where you probably should be a little bit aware about your signal's phase characteristics. So the first one is sound design using synthesizers and stuff like that. If you're constantly generating similar types of waveforms, you definitely should be aware that phase cancellation could be occurring, or even use it to your advantage to make something cool. Now, different synths approach phase adjustments in different ways. For example, Serum has its own little phase knob here, similar to what we had in a phase plant. So this one starts at 180 degrees, goes down to 0 and up to 360 degrees. But we also have this random knob here. And what this one does is it actually randomizes the phase of the oscillator every time you push a note. Now, this could be useful for a few different reasons. Maybe you just want less of a sort of digital sounding oscillator and you want it to sound slightly different every time you push a note. Having the random all the way up might be a good start. But also, if we bring the unison up here, notice that the random knob in Serum is at 100% by default. Remember how I said that unison works by duplicating the oscillator and slightly detuning each new voice? And we discovered that that actually causes phase cancellation. By having the random knob all the way up like this, you're randomizing the phase offset of each unison voice independently. So you get much less of a phase cancelled out sound, right? If I bring the random knob down, it's going to get a lot less broad and stable sounding and start sounding a lot more sort of comb filtered. That's all phase cancellation. Also, if you're using oscillators to modulate other oscillators, like for instance with FM or frequency modulation or even amplitude modulation, changing the phase of one of the oscillators can actually make a big difference in the sort of tone of your output signal. So in this phase plant patch, I just have one single sine wave that's been being modulated by another sine wave here, which is being modulated by another sine wave, which is being modulated by another sine wave. So it's a big stack of FM. Now, if I bring the modulation amount up here, you get this weird sort of tone, right? But now if I change the phase of just one of the oscillators, you get a big difference in tone. But outside of the realm of synths, maybe you're producing a track and you're wanting to layer together two different sounds, maybe, for example, a kick and an 808. If the phase relationship of those two things isn't quite lining up properly, odds are that it's going to end up sounding either a little too boomy or boxy, or it's going to sound a bit too thin and shallow due to like constructive or destructive interference. So dialing in the phase rotation of either the kick or the 808 so that they mix together seamlessly could actually be a great option. This is pretty popular as well in genres like psytrance when you have rolling bass lines that are static in pitch, and I've seen a lot of those producers kind of line up the rolling bass to the kick so it fits perfectly. So you could either do this by introducing a small delay to one of the instruments, or you could also change the phase offset of only the kick's sub-frequencies using an all-pass filter, like for example SSL's X phase or disperser or something like that, like we discovered earlier. It's also important to note though that this technique is almost always used in conjunction with sidechaining or volume automation, so that the body of the kick in this example and the start of the 808, for instance, aren't playing at the exact same time and sort of building up an amplitude with constructive interference. The phase alignment part of it is usually just to get the second instrument or signal to fade in as seamlessly as possible. Phase correction like this is also extremely common in like live recording scenarios, like for instance miking up drum kits and things like that. Since in these scenarios there's often multiple mics all miking up the same source signal, and each mic is a different distance away from that source signal, and the speed of sound is finite, right? And it's actually relatively slow. The sound will actually be reaching each mic at a slightly different point in time. So phase alignment in that instance is actually really useful as well. Also, another example is maybe you're trying to layer together two separate snare sounds to make your own new snare. And maybe the phase offset or polarity isn't quite matching in line with the other one. You could always try inverting the phase polarity with one of the signals to get them to sort of align a little bit better. And Ableton's utility device actually has that built in. So with these two L&R options here, you can flip the phase of either the left or the right channel separately. And this little symbol, I think it's like theta or something, it looks like a little zero. That's actually a signal that represents phase or polarity shifting generally in audio production. So whenever you see that, it means something's happening with the phase. It is important to note, though, that when you invert the phase like this, you're not actually moving the signal forward or back in time. You're simply just inverting the polarity of the waveform. So you're making peaks into troughs and troughs into peaks. And like I said, doing this is really, really common when you have just two signals that are occupying similar frequency ranges. And you'll often see a lot of producers just sort of messing around with flipping the phase polarity of different signals to see if they'll gel together a little bit better or not. And issues like that usually just manifest themselves as like a little bit of a loss in energy, especially with super transient heavy signals that don't really have a specific stable frequency attached to them. They're more just heavy transients. You'll usually just hear a little bit of a loss in energy rather than comb filtering or phasing like that. Another time you should be aware of like phase inconsistencies and stuff like that a little bit is when you have two copies of the same signal, like for instance with an aux send or a return track or whatever. If you start affecting that second signal differently to the first signal with effects that affect the phase a little bit, like high pass filters, for example, and you mix that slightly phase shifted signal back into the original signal, into your master bus, the end result is going to be a little bit of a phase cancellation or boost or whatever it might be. So you definitely have to be a little bit aware of that. But most of the time, these effects are usually pretty subtle. Some people will tell you to never ever EQ in parallel, no matter what you do ever, for this exact reason. But in reality, even if you do change the sound a little bit due to phase shifting and you don't realize it, a lot of people are just going to naturally adjust for that and compensate, even if they're not realizing they're doing it at the time, because usually the difference is just maybe a dB or two in the low end or whatever it is. So it can easily be compensated for. Some people will also tell you you can EQ in parallel, just make sure it's linear phase. But like I said earlier, linear phase EQs have their own problems with pre-ringing and stuff and like softening of the transients. So just be aware of that. Another time you might want to be interested in phase shift is when you have a plugin or device that utilizes separate bands. So for example, stuff like multi-band dynamics or OTT, for example. The signal's split up into three separate bands, right? Low, mid, and high. Or same story with like kilohertz multipass, for example. Since each cutoff point here is basically its own little high or low pass filter, some phase shifting is always going to occur in and around these sort of areas. And since these filters are kind of in parallel as well, like they're all sort of next to each other and we're hearing them all at the same time, the phase shift is also a tiny bit more noticeable than it would be with just like a single low pass filter. But again, it's still not the end of the world. It's not like it sounds horrible or anything like that. You just need to be aware that your signal will sound slightly different if you put multi-band dynamics or whatever on your track. Not necessarily worse, not necessarily better, just different. And most of the time, if you're using something like multi-band dynamics, it's to really improve the signal in a meaningful way. So usually that far outweighs any negative effect that shifting the phases slightly might have around these cutoff frequencies. So it's all a give and take. Need to be aware of things. You may have also seen things like correlation meters, like this is Voxengo's free correlometer plugin. All these are doing is measuring the polarity difference between two signals. For example, I've got two signals here. Both are a little drum loop that I've made, and both are exactly the same, so the polarities should be lining up perfectly. So each peak is a peak down here, and each trough is a trough down here, if that makes sense. So they should be constructively interfering. And I can feed this second signal here into correlometer via a sidechain input, and I'm going to make a corolometer compare the left channel in this first signal to the left channel in this sidechain input. So now I should expect to see on the corolometer that my signal is perfectly positively correlated. So you can see here on corolometer we have 0 in the middle, all the way up to +1, and then all the way down to -1. So +1 means perfectly positively correlated. -1 means perfectly negatively correlated. So they would be cancelling out in that instance. So yep, you can see they're both perfectly correlated. Now if I go to my second track at a utility and invert the phase of the left signal, now they should be perfectly anti-correlated. As it plays back, now each peak should be a trough in the second signal, and each trough in the first signal should be a peak in the second signal. And we should see this graph go all the way down to the bottom, and we should hear some weird phasing happening. Maybe we'll only hear the right-hand side, possibly. Yep. And it's perfectly negative. So that's what these corolometers do. Now, most often they're just used to compare the left and the right channels polarity. So I've set corolometer up here just to compare the left and right in one of the signals. And we can see it's pretty much perfectly correlated, apart from up in the high end, there's just a little bit of stereo width. So if the signal is hovering around the 0 here, that just means it's a super wide stereo signal, but there's not going to be much phase cancellation at all if we condense the signal down to mono. But if we were to see that the bass frequencies were like really, really negative here, that means if we were to play the signal through a mono speaker or at maybe a big stadium or something like that, I don't know, or a club, that the bass frequencies would probably end up cancelling out. And that's probably not what you want, especially for a big, powerful mix. One of the most important things is a big, strong low end. So multi-band correlation meters like this one show you the correlation of each frequency as well. So these are all separate band passes, each individual meter. Now you can also have single band correlation meters, and that's literally just what stereoscopes like Ozone Imager is doing. This is literally just a single band correlation meter. We just have amplitude on this axis that goes up and around, sort of thing like that. And then we have correlation as the left and right. So anything that's in between these two lines basically equates to being between 1 and 0 on this correlation meter here. And anything that goes beyond that equates to being negative. So if you go beyond there, then you'll start to have a little bit of phase cancellation. So that's pretty much all I have to say about phase for the moment. Hopefully it's not left anything to the imagination. Hopefully now you can sort of worry about what actually matters, make some good music, and not run around all paranoid wondering if your phase is good or not. If you didn't know, I have a Patreon where I upload exclusive videos, sample packs, tutorials, and all sorts of things. So if you got a spare few dollars per month, definitely have a look. It would be much appreciated. Thanks to all my existing patrons. You guys making these videos worthwhile. Thank you very much. If you have any questions about what I've covered in this video or what I should cover in the future, hit me up in the comments below or hit me up on my Discord server, which I'll link in the description. But until then, I'll see you guys in the next video. Thanks.